So here we go. So this is what I had to skip over yesterday. I wanted to illustrate how these elements about binding high-dimensional fields through joint neural representations, the coordinate transforms, and the binding through space, how those actually then enable higher cognition. And you will hear more about that in the special lectures that follow tomorrow and on Friday. But I want to give a first survey, and I'll be referring to this later on. So the first example, I'll go through two examples. The first contains these two elements, namely how you can perceptually ground relational concepts, and then how to actually generate such relational concept-based descriptions. And then the last point, the second example, will be about mental mapping. So let me first maybe clarify what I'm talking about when I talk about relational thinking and concepts and grounding. And so here you have an example, a language, a phrase that says red to the left of green. And if you hear that phrase and you see this sort of scene, then perceptually grounding that phrase means that you know that the speaker is talking about this red object here, and that this is the object that this is relative to. So this is a relational, a spatial relation, right, to the left of, and to the left of requires you to understand that there's a reference object, the green one, and for you to interpret that phrase, therefore you need to ground the reference object. So here, for instance, a field creates a peak of activation at some point that is centered on the rightward project object, the green one, and then a peak is generated on the leftmost object, the red one. You actually see the kernel of connectivity sort of by this shading pattern. That's what this decision is based on. This is a representation, and we will get to that, in which a coordinate transform is made, so that the kernel that indicates to the left of is centered in the reference object. That's why the spatial relations, the spatial metrics are a little bit different here. And this is actually the sort of the negative invert of that, which is used for a so-called condition of dissatisfaction that we will get to in the second part of today's talk. So perceptual grounding is this capacity to take a phrase that is represented by concepts and make sense of it perceptually, so linking to essentially visual search, to selective attention. Describing a scene would be the reverse of, for instance, if you just have that little scene and you're able to say red is to the left of green, then you're generating a relational phrase to describe that scene. So these two directions that we're talking about. This describing is, of course, a much richer phenomenon in terms of the cognition involved. For instance, you have to have some intention of what you want to communicate. This is a very trivial scene, so here it might be straightforward to do that. You might actually, if you see the scene, you would typically not even use a relational phrase, because you would just use the term, the red ball, because that is sufficient. And you would only use a relational phrase when you need that, when there are, for instance, two red balls, and you have to characterize the one that you mean by relating to maybe a unique reference object, or very perhaps very salient reference objects. We treat some such things in this theory that I'm not really then going into too deeply today. Daniel will do a little bit of that in his special lecture, and I'll refer to that again in a moment. So I'll focus more on the perceptual grounding part to make this clear. So this is the architecture that does that. We just published a paper. This was an early paper. It's available on the dynamicfieldtheory.org page, and the preprint of the paper that was just accepted about this is actually on the top of the list on the dynamicfieldtheory.org page. So have a look if you want. So this looks terrible, perhaps, right? Complex and so on, but you've already built some of that in your exercise, actually. And I'll just take you through that very briefly, and Daniel will take you through that in more detail and expand this. I take you through this briefly to just tell you what the ingredients are, and you will recognize that most of the ingredients are things you are familiar with by now, and especially there are these ingredients from high-dimensional fields. So The first thing is maybe the ingredient you're less familiar with, but a little bit, are these nodes, these concept nodes. So we have here, we have color concepts. So these are not actually metric or grounded perceptual outcomes. They are categories. So you have a node for red and a node for yellow, and that means this is supposed to be a color concept that is linked to the language concept. So we're not dealing so far in this theory with actual language processing. So there's a rich literature, huge literature on that, on how you can link auditory features to concepts or written features to concepts. So that's a very complex thing. So we're just taking for granted that somehow the output of that can activate categorical representations of a concept, like the red concept and the yellow concept. And we're dealing with how that is perceptually grounded by assuming that these nodes are linked to color representations. So for instance, here there are two fields. They are called intention and condition of satisfaction field. I'll explain in a moment. In the second lecture of today, I'll explain what the distinction between those is, but they are both fields over color as a dimension, and essentially there's a kernel of connectivity to these fields that enables grounding these concepts. So for instance, if yellow is activated, then a peak is induced over yellow that can then be projected elsewhere. And conversely, if you have a peak here, you can actually activate the yellow node. All of these connections are bidirectional. You see there's a line going in and a line going back. There are also, so every node here has two aspects, and Daniel will explain that better. One is sort of the memory, the working memory, like here, that's how you store the output of your language machine. And the other is when this gets actually into the foreground, when you're operating on it, the production node, if you wish. And there's also two versions of each of those, namely one, that concept as a reference, referring to a reference object, and that notion, that concept when it refers to a target object. This is the famous role, as in role filler binding, for instance, if those of you know these sort of things. Essentially, it's a form of syntactical structure where you assign a meaning. It's actually semantic. It's not really syntax in the language sense. It is the controls the meaning of these concepts, and these are two typical roles. There is a limited number of such roles. For instance, you could have two roles and subjects or agent roles and so on. And these are two roles that are two different kinds of object orientation that are very common in relations, in a lot of verbs, action concepts, right? You know, action, you have an agent that acts on some object, and sometimes with a third object, there will be a tool. And so we're assuming essentially anatomical binding of a concept to a role, and that means we have different neurons for the different combinations. So when red is a reference, we have a neuron, and when red is a target, we have a different neuron, right? That's a specific assumption that we're making. So more will be said about that by Daniel. Here is the visual search machine. It's a simplified version of that visual search machine where you have the visual input, you have feature space field. So this is color over space. This is movement direction over space. Movement can be extracted, is actually extracted here from the visual scene. We have a motion detection system that I'm not explaining. And that's how we can ground things like moving to an object or moving away from an object. There's always two copies of the field, the one that's selective and another one that's a working memory, a scene system that serve some purpose that I'm not going to go into. These are the relational concepts. Again, the relational concepts are nodes, again, with memory and production version of it. And they are grounded through a pattern of synaptic connectivity that is now, for the colors, it was just a little Gaussian connectivity pattern. For these spatial and movement concepts, it's a pattern of synaptic connectivity, that makes some sense. You see, for above, you have excitatory connections here on the top and nothing at the bottom, below, left, right. And this is actually refers to movement space, which I'll point out later. So then away and toward has a similar structure. Now, I have to say, which space does this refer to, right? The color concepts project onto hue space. It's very trivial here. Which space does that refer to? Well, it refers to a space that we call a relational space. And that's a space that is centered in a reference object. So you can apply these kernels here to the center of this, and you coordinate transform the original space to be of the right kind. So for instance, when you're taking spatial reference, left, above, and so on, and then you have a reference representation and a target representation. And this little triangle is that coordinate transform that I explained earlier, or I mean yesterday in the lecture, and that, that will steer the transform of the target field to be centered on the reference field. For instance, right now this reference object is present, and this is this part that is here inhibited, and these three objects will then be represented here centered in that reference object. The reference object would be here in the center of this field. And that's how, applying these operators will actually, you have a single set of connectivities, a single set of these operators, and you can apply them across the visual array by shifting the array around. That's the key idea of here, rather than have, for instance, a copy of that connectivity for every possible location of the reference object, which would be sort of the deep learning kind of approach of weight sharing, of applying, of having a lot of redundant synaptic connectivity. So that's a much simpler assumption. For movement direction, it's a little more complex. I'm not fully explaining that. For movement direction, what you have to do is use a object-centered orientation. So if an object is moving, then you're making a coordinate transforms that amounts to rotation. It's actually translation in polar coordinates, log polar coordinates. You can see that the translation is the same as rotation. And therefore, when you're centering the field such that the movement direction points in the vertical direction here, and that's how this kind of operator can capture toward, and this one can capture away, because it's actually centered such that the reference object is here on top or here on bottom. Yeah, that's the elements in here. So I'll just show you this one simulation, which is sort of the most interesting case that illustrates a point. So this is a scene. We're just looking at color, so it doesn't know about screwdrivers. Red to the left of green is the phrase we want to ground. And this is an interesting phrase because this object will be the correct target. Here's a green. It's interesting because there's another green here, but there is nothing to the left of that. And there's another red that you could confuse with that. And so what actually happens here in this simulation is that this object will be activated first because it's a little closer to the camera. It's larger, more salient. It will be more likely to be selected as a reference object. You see here the attentional activation of the reference objects. These two objects that match in color. Now the reference concept is green, already activated at this point in time. And what we have to have is that the system finds that there is nothing to the left of it. And we will see here that will happen through this condition of dissatisfaction. I'll explain in the next lecture how that actually works. So this is shows up here the kernel for to the left of. The left of was activated here as stored in memory as the relational term. The red is stored here as the concept for the target. And so you will see in a moment that here the reference object has been actually selected here. Actually, this is the object. It's this one. Sorry, this one has been selected as a target object. And now we'll see there is nothing that hits this, but there are some things that hit this region here, like non-matching objects. And as a result, the system decides that this is not a good reference object, and it will ultimately inhibit this object. And then in the next step, we'll find this, a green reference object. And then once it has that, it will be able to select among these two targets the correct one, which would be the one here on the left top. That's how the system answers and actually able to, so it has intentionally selected the correct object. You know, it's by this object hitting here the correct cone of activity. So Daniel will explain this better than I do. My point is, to show you the principle, but it's also interesting that there is the sequence of events, right? There is actually hypothesis testing in a sense. You're first activating something wrong, then you're rejecting that hypothesis, going to something else. That is really mental, right? That is really cognition. It's no longer, you know, sensory motor as such. And so how that happens autonomously in time, how you go from one to the next, deactivate and then activate again, and so on. That will be now the next topic. That's the autonomy topic that I'm very interested in. Okay, that's the main point I wanted to make about this first example. I want to push this one step further. This is something we have only published in a short paper form. We're working on this. You could think this is still an example. It's still sensory motor in the sense it's still perceptual grounding. So you're still doing, you know, attentional selection. So you're directly operating on a visual scene. So is that really cognition? So here is the next step. This is inspired by work out of the Knauf lab in Gießen. And there's a whole literature on this for those who know that. This is what's sometimes referred to as mental mapping. So now you're taking a participant and just telling that participant things through a set of propositions. So for, you know, translated in our terms, you would say to people something about colored objects. Let's say there's a cyan object above the green. Cyan, I'm sure nobody would really say that, but that's one of the colors that we have in the Apple color selection. There's a red object to the left of the green object, and so on. And then you ask people, where's the blue object relative to the red object, for instance. If you don't attend to this carefully, you can't really answer the question. This really requires attention and mental processing. And in fact, that's what mental mapping is about. And it's not well known that this doesn't happen automatically. It actually is not driven primarily by your thinking about how objects appear visually. It's really about understanding conceptually what objects are. So the actual experimental examples are usually not these very indiscriminate things like colored objects. It's typically categories, like for instance, there's an example with cars, like the BMW is parked to the left of the Mercedes-Benz and things like that. That makes it easier for participants to actually do that. There's a lot of subtle stuff known about that. And I will illustrate one aspect of that is known in the literature, a very nice review paper that reports that. So the architecture for doing that is pretty much the same. So this looks very much like what I just showed. It is a bit simplified because we dropped the motion part and some simplifications in here. The one major simplification is there's no visual input, right? This is, so the idea would be, of course, it's the same architecture, but now we're not using the visual input. So, you know, the scene representation was previously fed by the visual input. So the one new ingredient or different ingredient is that we have a mental map. A mental map is now a purely spatial representation. It's actually something that was also in the previous model, but didn't play that role. It's a spatial representation in which there are memory peaks that, so sustained working memory, sustained peaks of activation that summarize what we have accumulated in memory. They point to feature-based, feature space representations. In this case, only one, but you could do this across multiple features, and that will be then, in terms of binding through space, a mental map that's a scene representation, but it's a scene that you only mentally constructed. And so what happens in the model is that, these peaks here are not induced by the sensor input that comes into scene representation, but they're induced by applying the operators here directly to the relational field. For instance, if you say to the left off, and you have activated, the first object that you mentioned will be just put into the center of the field, but again, a boost will create a peak, and that will be put into the center of the target field, and that will be entered here into the map into the center. And any color feature that you associate with it is associated by putting in the corresponding slice, where the location and the slice overlap, and that's where a peak is formed, and then you will store, let's say, the scene object, scene is to the left of something else, and the scene object is put in the center of the scene that way. And then when you specify the relational, the reference object, create a peak here that will be then guided by the operator, and it will be this relational synaptic pattern that will dictate where in this field the peak will arise. For the first one, it's very simple. If you have to the left of, it will be somewhere in that cone of connectivity that a peak will arise. That peak will be, again, inserted here, goes up through this entire diagram, then be inserted here in the spatial map. When you already have peaks in the memory, they will show up, because you're projecting from this into the relational field. So you see these little shadows here, they will act as inhibition and will prevent the system from putting a peak in the same location. That's how you keep the peak separate. So that's the only new ingredient in this here. And I'll just illustrate that here. Again, there's a lot of stuff here, We have the concepts, relational, spatial, the target color. And this is a case, actually, I thought I had, I wanted this slide first. Yes, sorry. This is when you built the map. So the model has already previously experienced a statement about cyan, about red, and about green. I put the labels here just to say that these spatial locations through the binding through space are associated with those colors. And it's currently getting the phrase blue to the right of red. That is an ambiguous phrase in the sense that previously you already put green to the right of red. So then I have to decide where to put blue. And a psychophysical observation in these kind of studies is that people put them outside the previous map so as not to disturb, let's say, the previous pairing. And that's what the model does, spontaneously does that just through the properties of these kernels. And these kernels originally were actually motivated by psychophysics about people rating how good an example of left off, right off, above, and so on a particular configuration is. So the machinery of creating that peak, I'm not going to explain that in a lot of detail, relies on the kernel, the spatial kernel, creating a peak in the target field, and it will do that at some moment here in time, right now. So it has to determine that is sort of the free location for the peak. Once to the right of is applied, and it will enter that peak here in the map. So that's, again, that peak is linked to the corresponding feature dimension, and that's how you know it's blue. And so once you have that, now you can do inference. Where's the blue relative to the green? That just means setting in memory the corresponding concepts. And now what you do is perceptual grounding of that phrase, but it's grounded on the memory, the scene memory that's in your mental map, not on visual input. And so in this, using the same kind of techniques, it's literally the same model, and it will be able to do the selection. So blue relative to green, that should be should answer to the left, to the right of, right? Blue relative to the green, to the right of. So it's actually answering here to the right of. You see a little bit the kernel here as a shadow. So that's the highest I'm going to go or went in this lecture about higher cognition, right? That's about as high as we got. I'll point in the end, I'll point to further directions that we're going. Good. That's the little part I wanted to complete from yesterday's lecture. And what I want to do now is ask how the autonomous processing, the unfolding happens here, right? In this mental mapping, it's very clear that there is no input. This is not input driven. This is all just taking place in your head. So taking place in this neurodynamic architecture. That's what we're getting at, right? So we think it's a big distortion that in connections, thinking about cognition, so many things are dependent on input. In the first approximation, a lot of it is actually just input-output mapping, and then there's a little bit of recurrency for some purposes, but it's not very well understood. And so here we're trying to see how things that look like algorithms being performed, where you test hypotheses, reject them, and so on, how that actually emerges from neurodynamics. That's the next topic I'll be talking about.